Guidelines. My name is Willard Dion, and I will be giving the presentation along with Danker Coling. What we'll be talking, I'll give you a little bit of an outline here. We will introduce the funding for the project, which was a BRACE. I'll introduce the existing guidelines and list the objectives. I'll talk about our schedule, which of course has been impacted now by COVID-19. And I'll give some examples of climate change impact issues in Atlantic Canada. And then Danker will take over and talk about the guidelines, the next steps, and feedback and questions. So the project is supported or funded by Natural Resources Canada. The BRACE program, Building Regional Adaptation Capacity and Expertise. It's a 5-year program, $18 million. And as it mentions here, is to increase the ability of communities, organizations to access, use, and apply knowledge and tools on climate change adaptation in their work. There are currently 19, not 18, I checked today. There's 19 projects under funding, 8 of which are in Atlantic Canada. We are the only ones doing guidelines. There's a variety of work being done from forest to agriculture to whatever, but we are the only ones doing guidelines. And we have been involved to a little extent with a project in Newfoundland, and we were to be involved with a project in PEI, but that was cancelled because of COVID. So the guidelines are here. Those of you who are in the business of water and wastewater, or water anyway, have seen the original guidelines published in 2004. And we've now since March have a draft of the new guidelines. The lead on the water guidelines is Mike Chalk, and we had 11 engineers and 1 hydrogeologist involved in updating those guidelines. And the wastewater guidelines were initially started in Nova Scotia in 1991, adopted by Atlantic Canada in 2000, and then revised again in 2006. And they have been out for comments since April. So we had 3 guidelines, 3 objectives on the project. One was to incorporate climate resilience, and we'll be talking about that later on. The second one was to include a chapter on climate change or climate resilience, and Danker again will be talking about that one later on. And the third objective, which was a big one for Natural Resources Canada, was capacity building through workshops, webinars, and dissemination of information. So this is what we're doing today. We're talking about climate change, but it's actually under the topic of capacity building. So some of the things that we should mention, and Danker will talk about these things, is that climate change is constantly evolving. There's new data, new research, technology programs coming all the time. We need to understand the global, regional climate trends. And again, the science and the climate are both evolving simultaneously. So what Danker will be talking about later on is that the guidelines should be a living document. We are going to reference other active standards, and they're coming out of the woodwork now, left and right. There was very little when we started this project, but we're seeing more and more documents related to climate change in water and wastewater coming out. And we're going to focus on the process, not the specific data points. So our target audience, of course, are technical people, the consulting engineers who are the designers, the utility and public works personnel who are the owners, and the equipment and service providers who are the suppliers. And the other target audience, of course, are the municipal administrators and municipal councils, because they are the ones that everyone eventually reports to. They pay the dollars, and they are, in fact, in charge at the end. So capacity building, as I mentioned before, is a major component of this project. It involves conference presentations, workshops, and webinars. And we want to make sure that the stakeholders are aware of the climate change, the sources of data, the available training. And there's a document, it's been out for a while. PIVC has been out for a while for engineers to take a course on climate change. And to start things off, in July of 2019, we established a web portal on the ACWWA site. What it does, it provides a platform for stakeholders to upload and download documents that relate to climate change or to the wastewater guidelines. We have about a dozen documents there now. We got the new guidelines, we got the old guidelines, and we got some guidelines from Alberta, from 10 states, from Quebec, and I forget, Manitoba, Saskatchewan. And we're seeing a good interest in downloads. I monitor the downloads on a daily basis, and I can see the downloads increase after something has happened. So when Danker went to Vancouver in February and gave a presentation, there was an uptick in downloads. And then we had increase in downloads after we published each of the manuals and after we notified the stakeholders. So the stakeholders are, of course, ACWWA members, which are mainly, a lot of them are engineers. The Maritime Provinces Water and Wastewater Association is the operators group, although some engineers do belong to that one, and operators do belong to AC also. But those are the main two groups. And of course, we got the consulting engineers from all 4 provinces. We got the suppliers, the Atlantic branch equipment suppliers. And then we made contact with the Municipal Public Works Association of Nova Scotia and the Canadian Public Works Association of Atlantic Canada and of Newfoundland. And this last time we made contact with the engineering associations. So our contact list is quite extensive. If we're missing somebody, I'm not sure where they are or who they are. So just briefly about the delivery and the timelines. As far as the delivery is concerned, we are working, CBCL is working for a committee. The water supply lead is Wendy Crossack. The wastewater lead is Richard McEwen. They are owners. And then there is, of course, Clara Shea provides support for the Atlantic Canada Association. And then we got one provincial rep for each of the 4 provinces. So for Nova Scotia, the rep is John Lamb. The deliverables, as per the terms of reference, of course, we had committee meetings. We had to deliver draft guidelines. We had to deliver 4 workshops. One has been held, but the rest have been canceled due to COVID. We were to present to two national conferences, and Danker did go to one in Vancouver in February. The second one in November in Niagara Falls has been postponed. And then we had established a non-technical webinar with the Atlantic Mayors Congress, and that was canceled. Most of these things were to be held, except for the second national conferences. Most of these presentations were to have been held in April. So there's going to be a little bit of repetition here. So basically, the original completion date was late fall 2020. Again, because of COVID, we've done many changes. So now the workshops are going to be webinars. Not this one. This is an extra one over the webinars. The project committee members are restricted, by working from home, travel, and mass gathering restrictions. And we are going to have a meeting soon to discuss the schedule. But right now, as we speak, comments on the drafts are due the end of August. Now that may change once the committee meets, but right now we're looking at comments the end of August, and we're looking at a completion date in the spring or summer of 2021. So, talking about climate change. Are we concerned about climate change in Atlantic Canada? Yes, we are, and I'm going to run through some examples here. We all remember storms, but we don't remember all in a row. But basically, in the recent years, we've had winter freezing rain and severe snowstorms, and we had power outages at water plants, wastewater plants, pump stations. We've seen increased spring flooding, and we've seen fall hurricanes and severe rain events all season, not just during hurricane season. So these are notable events. Some of you may remember one or two, but maybe you don't remember them all. We got Hurricane Juan, we got White Juan, we got Igor in Newfoundland. In 2016, we had droughts and flooding in Sydney. In 2017, we had the New Brunswick ice storm, and that was blamed on the fact that New Brunswick should have been colder, like it usually was, with snow, but it was warmer, and they got the ice. The same year, New Brunswick got a drought. Sydney flooded again in 2018. New Brunswick floods, of course, in 2018. Then we had droughts. And then, of course, Hurricane Dorian came in 2019. Some of the headlines from Hurricane Dorian, in the newspaper that 38 communities were impacted by power outages. People had to resort to mobile generators and pump stations and pump trucks to pump out power stations without power. A rogue wave was detected near Newfoundland, a record wave of 100-foot meter wave near Newfoundland. And about the same time, for the first time ever, the Lunenburg Wastewater Treatment Plant flooded. And very close to having electrical equipment affected. Again, with Dorian, we had communities without water. No water means you can't fight fires. And as a result, after Dorian, people are starting to buy generators and trying to gear up to be ready for the next time around. So I'm just going to go through some examples of events that we've had in Nova Scotia or in Atlantic Canada. Of course, we always have the St. John River flooding. It's a yearly event. I actually went to UNB in 1974 when I graduated. My thesis was a routing of the St. John River flood of 1973. So it's flooded back then, it's flooding now, it's flooding even worse now, I think. So of course, when we have floods like these, we have inflow into the collection systems, we got submerged pump stations, we got entire wastewater treatment plants flooded, and of course, on a river system like this, if there's a water supply down the river, of course, it's probably being impacted. Here's a small wastewater treatment plant with a red roof. You can see the building in the middle, and right behind it, you can see kind of a white, that's an aerated treatment plant. And under aerial view, the building is right here, and there's a treatment plant. And here it is under flooding conditions. There was a pump station right next to it that was flooded, but the top of the plant was just barely above flood water, but it didn't make any difference. Everything else was flooded. Here's a pump station in New Brunswick, probably where they are aware of flooding. So the platform is actually raised, where the operator can actually handle the pump station without walking in water when it's flooded. Here we have a groundwater source that's been flooded. Of course, we like to keep our wells dry. The ground around it should be dry because otherwise we have influence from surface water, but this one is flooded. Here we have a wastewater lagoon. You can see the control building. You can see two lagoons over here. Just keep your eye on this fence. Here it is under flooding conditions. Totally flooded. This one was just one of two in the same region. And there were some more. And this was during the St. John River St. John River flood. So you can see the impact of that one. Here we have a surface water plant that was built, a water treatment plant that was constructed near the source of the water. You can see from the road that we're quite high, so there's a good elevation between where the picture was taken to where the plant was. But anyway, it was near the water and it flooded. So of course, with climate change, we would be looking at this. We'd be looking at locating the plant higher, or even putting a raw water pumping station by the lake and pumping up real high to the plant. But those are options that would have to be looked at on a specific project. And we have flooding not only when we put infrastructure near water, we also have it when we think we're inland. Well, when we are inland, here's a wastewater lift station that has flooded. Here is this is a real project I was involved with to protect the innocent. I wasn't allowed to take a picture, so we drew it up. But here is a gravity sewer that leaks, discharging into a pump station. Under low tide, everything is fine. Under ordinary high tide, we have leakage into the manhole, and under surge tide, the entire manhole, the entire street is submerged with water, and this happens, a couple of times a year. And we found this one out. It was a small pump station, the end of a collection system, the far end of a collection system. It should only be. It was only servicing maybe 6-7 homes, so it should have been working very little. But when we looked at the records, it was working all the time, and we were able to determine through power records and pump meter readings that it was working all the time rather than intermittently for a few homes. Again, here is a wastewater pump station. Again, when you look at the topography, it's nowhere near water, but obviously, it's a low point. And this pump station, you can see here, the electrical components were almost affected. This pump station has now been relocated. And here's another one, again, in what would appear to be, inland, a water pump station that was used to boost the water to a higher elevation. Again, that one is all flooded. So those were examples of flooding. On the other hand, climate change is giving us drought and heat. As a result, we got mandatory or voluntary water conservation requirements. With low water quality changes, so we have water treatment issues sometimes. There are some utilities that have to maintain a minimum flow for DFO, and they have problems meeting that when they are in a drought condition. Again, when there's a drought, the demand for bulk municipal water increases because the people from the country have to get water from somewhere, and the water haulers get it from a municipal system. We have in wastewater collection systems, we got septic conditions because the flow is low and the sewage doesn't get to the plant in time. And then when it does get to the plant and it's septic, then we have operational issues at the treatment plants. And looking at some of the older plants, especially for schools and community centers that were built 30, 40 years ago, they discharge into a brook or something. And with drought and heat, we find that they are just discharging into a dry ditch now. Here's an example of a surface water supply. May, you can see what it looks like. In October, you can see it's fairly dry. And of course, when we get dry conditions, we are now getting blue-green algae. And more recently, we know that from news articles that dogs have died after drinking water in the St. John River. There have been some advisories in Dartmouth, Bedford, and Inverness County of blue-green algae. And one treatment plant in Moncton, of course, is taking the steps right now to upgrade the water treatment process to accommodate the blue-green algae. And we expect there's going to be more plants that's going to have blue-green algae. And of course, we're updating the guidelines to include a chapter or a section on blue-green algae and treatment. So here's an example of algae when this is the same water supply I was showing you before. When the water is low, the algae comes out nice and green. So just to wrap up my my section, how hot was it in 2019? We had the warmest June, July, and September on record. August was the second warmest month on record, and it was the warmest summer in the Northern Hemisphere. And then if you look at the last number of years, you can see in the last 6 years, we've had the 6 hottest years on record. The hottest year being 2016. And from what I've been hearing, Danker will probably tell us a little bit different, more if he knows more, but what I've been hearing is that 2020 is on course to take over as being #1, as the hottest year on record. So that finishes my presentation. I will now pass it over to Danker, who will focus on climate change.
Great, thank you very much, Willard. I think that really sets the stage with some great examples as to why this topic is important. So I'll move right ahead into climate resiliency and incorporating that into a guideline document. So as Willard previously mentioned, the current guidelines do not include any mention of climate change or climate resilience in general. One of the challenges, of course, with incorporating this topic is that it's usually a very multidisciplinary topic with a lot of professionals involved. Can be relatively complex. So putting it into a guideline document, striking a balance between something that is user-friendly, that is in line with the rest of the guideline document, while at the same time also striking the right sort of technical and scientific balance as well. So I should note that the current guidelines that are on the web are version 2 of version 4. We envision certainly that the final version that is published at the end of this next spring or summer will look quite different. The important part is getting feedback, getting commentary on these guidelines. So before I get into this, I really encourage everyone to have a look, download the document, and also, any and all feedback will be taken very seriously, will be incorporated. This is your document, and it needs to be, helpful and valuable for the community. So I certainly encourage that before I get into this, and also note that it's still very much a draft. So we're very much open to change. So with climate resilient infrastructure, which is really what this is about, and that was also our mandate through the BRACE funding program, we really want to look at infrastructure that is both planned, designed, built, and operated in a way that not only anticipates but prepares for and adapts to changing climate conditions, as it says there. Historically, the previous guidelines really only considered historical data, so looking at past events. Whereas moving forward, what we want to do is have the practitioners look at both historical data and also projected future data. So that is data generated by climate models. So that'll be quite a change going forward in the way that the material is presented in the guideline. I am aware that most people already practice this professionally within projects, so it shouldn't be a big change on a professional level. It's more just that we need to reflect this now in these documents. So updating the guidelines. We've really tackled this a couple different ways. But first, it's important to note that the guidelines cover a very large region. Atlantic Canada, as you all know, is a very diverse region, from Newfoundland to Labrador all the way to, of course, New Brunswick and PEI and Nova Scotia. So across this region, there is quite a large variation in climate projections and anticipated climate change impacts, and then therefore also the required responses. So it's very difficult to generalize over the entire region itself, and that has to be stressed in the document, which also means that we can't simply state the requirements for Nova Scotia. We have to think of it in broader terms. So to do that, what we're really going to be doing in this guideline is to present strategies and adaptation strategies that can be used in the infrastructure planning and design. So where are climate science resources available? How do you apply these climate resources? How do you then incorporate these into a adaptation planning or design or operational model? So the other thing, of course, is that these methods have to be reputable and reliable. And as Willard already previously mentioned, a lot of these are being updated and changed frequently. So we also don't want to put something in this document that will be out of date or superseded the moment it's published. So that's another thing that's really important to think about. So what we have in this document is two main components of how we are going to address climate change. We are going to incorporate a new chapter in the guidelines that is an introductory chapter. So basically, this will set the stage and set the tone for the reader for the rest of the document. The idea here is that before diving into the revised document in each chapter, where we will include references to climate change, the reader can reference this initial chapter with some guiding principles. So how do we address climate change into the guidelines? We'll have a little discussion on adaptation versus mitigation, which we'll talk about more in this webinar as well. Quite a large discussion on climate change data, which is very important. So what is it? How is it generated? Where do I get it? How do I apply it? We're not going to be providing climate projections directly in this document. We're more going to be talking about how to use it and where to get it. A lot of you probably already know this, but it's nice to have it kind of in one place summarized with some good sources. The other main component that will be in this introductory chapter is talking a little bit about the vulnerability assessments. Probably a lot of you are aware of the PIVC protocol. That's not something that we can present in this document since it is administered by, I believe it used to be Engineers Canada. It's recently been migrated over to a different organization. But the whole concept of vulnerability and risk assessments with the climate change lens is extremely important and allows asset managers and engineers to make decisions as to where adaptation strategies are needed. So that'll be addressed. And then, of course, every good document does need some examples and resources, so we'll be presenting those as well. So then the second component of this is, of course, how climate change is addressed throughout the chapters. So each individual chapter has been assessed, and in all the sections where required, updates have been made or initial revisions have been made to incorporate the considerations of future climate as opposed to looking at historical climate events. And again, I want to stress here that we are not going to ignore the past. We want to emphasize the importance of looking both at past and future weather events. So that's really the two main components of this revision. So the introductory chapter, I think today I'll spend most of my time on this. Really what it is, there's 10 pieces to this chapter. So the first thing is really a general introduction to climate change adaptation in the guideline. This should give the reader a sense of what the chapter is about and what they'll get out of it. Then the second one is the scope of climate change adaptation in the guideline itself. So really the key part here is recognizing that adaptation takes many different forms. Each community is very different. Of course, within the Atlantic region, we have a lot of very small communities, and then of course several larger hubs. The strategies will be very project-specific, site-specific, provincially, dependent on the programs. There is not a one-size-fits-all adaptation strategy, and it's extremely important to recognize that. Not every project needs a full-blown PIVC assessment or in-depth vulnerability assessment. Perhaps it needs components or elements of that. So what we're trying to do here is set the stage for what is the scope, what scope should be applied of these assessments. You don't want to create financial burdens for small communities, but at the same time, these topics have to be considered. So that's really the goal there. It's to give some guidance on what aspects of climate change adaptation and these kinds of assessments should be incorporated and to what scale of project is that applicable. Then the next one, we really want to talk a little bit about climate change projections for use by engineers. And really what we're doing here is giving an introduction about different types of climate models that are available, from global climate models to regional climate models, the uses of climate data, talking a little bit about the difference between an index and index and a parameter. We want to address the uncertainties associated with use of climate data. Of course, the further you project into the future, the more uncertainty there is with these projections, which has to be captured. How do you deal with that? Climate data in general and climate research is very much a live field that constantly changes. There's a lot of new research every year, and this definitely has an impact on the practice as well. So how do you navigate that? That's certainly something that we try and answer in that section. Then we actually give a brief overview of some of the anticipated broader climate change trends that we can expect globally and nationally. And this is really to give context. And it's not necessarily that these numbers will be used probably in an assessment, but we want the reader to understand that there are global and national changes, and then we take that down to an Atlantic level for every province. So within the province, at every different site, there are going to be specific climate change impacts, but we want to give the reader of this guideline a bit of a feel for what's happening in the next 100 years, where are we headed. Broad brushstrokes, I call it, for presenting that information. Then what we do is we provide a pretty comprehensive list of examples of climate change impacts on both water and wastewater infrastructure. This is definitely a list that's a work in progress, and we can continue to add to that over time as this is a living document. After that, we go into a section that elaborates on how do you identify climate risks, and this really comes down to things like a top-down versus bottom-up climate risk analysis, similar to the PIVC. And then finally, we do present some adaptation strategies to climate change for both water and wastewater infrastructure. Some examples again. Then we provide sort of a general list of indices and parameters for consideration for your project. So this is really just a starting point. What parameters should you be thinking about? What are important climate indices that could help you out on your project? So that's the purpose of that section. And finally, we present 5 different sources of climate data. We describe those sources, and we tell you where to get the data and some of the limitations of that as well. So that's the introductory chapter that we have incorporated. So it's really important to set the ground, I guess, set the stage for what this chapter does and what it doesn't do, because it's certainly, it's definitely not perfect, and it's going to need quite a bit of revisions, I believe. It's a start. So really what this chapter does, it gives a little bit of an introduction to climate change in Atlantic Canada and in use of design standards. It provides a framework mainly for implementing climate change resiliency and adaptation measures. It provides some examples of impacts and also adaptation measures. It will point you to climate change data sources, but it will not provide you with climate change data points to use in your designs. And it really is a foundational chapter for the rest of the guidelines, setting the stage for other pieces within the whole document itself. So what this chapter does not do, it doesn't provide very in-depth design specifics. If you're looking for a recommendation on the elevation of a pump station, it will not tell you that in this introductory chapter. It does not provide, again, what I was trying to say, a list of indices or parameters for your project at your specific site. It does not focus on climate change mitigation. This chapter focuses on adaptation. I'll get into that a little bit later, but a part of that also has to do with the focus of the BRACE program, which is where we chose to look at adaptation. The other thing is it doesn't really tell you how to analyze and assess large climate data sets. Climate data can be extremely complex to handle. These data sets are gigabytes to terabytes of data. And a lot of times the information that's used by engineers is a synthesized version down to values that are quantifiable for use in design. So it's not going to tell you how to go through those steps. That in itself is a separate field. So again, I wanted to bring up mitigation versus adaptation. So as many of you know, mitigation is sort of reducing the impacts of climate change. So This really has to do a lot with greenhouse gas reduction, whereas adaptation is adapting to a life in a changing climate. So this involves adjusting actual or expected future climate. So examples of those, mitigation, the classic one is reducing energy demand. And of course, inherently, I think what we want to do in this guideline is we want to, of course, promote that these facilities or various infrastructure components are operated in an energy efficient way. And that's always a discussion that is had in any project. But that is also a question of economics and a question of good design. And although it'll be touched on, it won't be the main focus of this chapter. The main focus really will be on adaptation. And this is really talking about adjusting existing and future infrastructure designs to deal with some of these climate change pressures. And not only that, it's also to do with maintenance, training, planning tools, so pretty comprehensive. So to set the stage, you will find that this guideline really does focus on adaptation versus mitigation, although we do not ignore mitigation. That is also important to note. So some of the key messages, again, we've touched on this already in the webinar, but historical observations can no longer be truly relied on. I think the uncertainty and the limitations associated with the uncertainty of climate models and their projections really has to be properly understood. Picking a number out of a climate model, even one, will not probably serve you very well unless it's very well understood why you're picking that model and why you're picking that number. So that definitely presents a risk when using climate data, and we'll talk a little bit more about that. And the guideline itself also speaks to that. So really what it comes down to is that using climate projections and climate data requires quite a bit of collaboration with climate scientists or engineers that have a good background in climate data. This is tricky because larger projects can afford this kind of interaction with various experts and teams. But for smaller systems at a small community level, often those kinds of costs are not in line with the project. So there has to be a middle ground. And I think we really want to emphasize that as well in those places where people cannot assemble a large team of experts to study climate impacts, but still want to consider changing climate. So the other thing, of course, is that climate science, making it transparent to engineers is a really big part as well. It's a two-way street. So practicing engineers, project stakeholders, and policy and decision makers should be informed about the uncertainties of projections. And really that's one of the key pieces we're trying to address in this guideline. So climate projections for engineers, the section really, as I said, we focus on global models and regional models. We talk a little bit about how climate models have evolved over time and the uncertainty. So here you see a nice graphic of really how climate models have gotten much more complex since the 1960s to present day. You see that it started with some very basic parameters, mainly to do with the ocean and the atmosphere, and then we've kept adding more and more complex components to it to improve the accuracy of these climate models. And to give you some perspective, a global climate model typically has it's a computational model that covers the entire Earth in grid cells, and these are points, and at each point the computation is made, a series of equations, whether they're atmospheric or oceanographic. And Nova Scotia, for example, pretty much fits into one square, probably two squares, and PEI is just in the middle of this one big square. So it doesn't really give you very good resolution, and it really generalizes the climate over an extremely large area. So we do have regional climate models, which I'll get into. The other thing, of course, is that we have the IPCC common representative pathways, which are often used, and these are projections for future scenarios based on emissions. So emission scenarios, and they're commonly referred to as RCP 1.9 through 8.5. And some of these scenarios say, well, there's a world with the reduced emissions, and there's a world where we start slowly declining our emissions. And then there's, of course, the scenarios where we have increasing emissions. What I find very interesting of this is that we've all heard of the Paris Agreement in 2016, and they actually have a scenario there that's well below 2 degrees Celsius, and they are actually pursuing below 1.5 degrees Celsius. So you can see it's a pretty aggressive target with declining emissions. So that's some good perspective as to what they're hoping to do. So the way to try and deal with some of this uncertainty that's created with these large global models is to look at regional models. So this is some examples, the CAN RCM4 model or the Parisi's model. Again, now we're going down to a 25-kilometer resolution, which gives a much higher resolution in Nova Scotia, as you can see in that little example there. And these models are actually driven by global models. So the global models feed data into these regional models. They're still very cumbersome, computationally expensive models. So they're run on usually clusters or supercomputers, and the data is available for download, but again, quite cumbersome to work with this data. And then the main thing about this data, of course, is the uncertainty. So worldwide, there are over 30 different climate models, and every climate model has a slightly different projection, and that's because they use different sets of equations or different sets of assumptions. And in theory, this is all very good. We want to have many scenarios available to us to understand the variability. The problem is, what do we take out of these models? So often what they do is they add all these models together, and they something called ensemble averaging to see what the average trends are of all these models. Uncertainty can be caused also by which kinds of processes are turned on and off in models. So these are all things that make climate data variable and more complex to use and increase the uncertainty of climate data. So we want to address that a little bit in this chapter to make people aware of what that means in terms of risk for selecting climate parameters and what you should be looking for. So some data sources. So again, you have these global climate models, regional climate models, and then you can do something called statistical downscaling to a specific site, sometimes using historical data at a particular site. And you can extrapolate some trends. So these are different ways of taking data from a very large area and moving it down to a project-specific site. But I think the main thing that is really important here, it's really easy to get lost in all this, and it's really easy to go down either the wrong path or to really get stuck in terms of what do I do, what do I use. And certainly what we found in projects, it's extremely important to consult someone who's an expert in this, whether it's a engineer or a scientist. Navigating these kinds of data sets is challenging. So there are sources available that are relatively simple to use and access, which I will show at the end of this presentation. But even then, in that case, it's good to consult with somebody as to whether you're using the right data. And again, I want to go back to that discussion. It's not all projects can handle that kind of involvement of multiple experts, but even at a preliminary level, it's good to try and do that. So the next part that we do is we talk a little bit about global and national climate change trends. So this is a very high level presentation of just what can we expect, as I mentioned before. Then we talk about specifically Atlantic Canada. So we talk about things that we know are going to change, things that we think are likely to change, and then things that are really unknown because of this variability and this uncertainty in the climate projections. So we do know that we're going to get more extreme temperature in the region. We do know that we're going to have changes in precipitation intensity. In Labrador and northern parts of Labrador, we can expect to have some melting of permafrost. And one of the ones that's probably very well described and studied is sea level rise, and also with we have issues associated as well with the rebound of in particular areas which actually increase the effects of sea level rise. So these are ones that we know are going to change, and we have a lot more comfort in the projections of those. Things that are likely are going to change is increases in freezing rain, decreases in snow, and increases in wave energy at the coast. And then things that are a little bit unknown are things like wind, things like sometimes fog even, the visibility issues. These are things that are more difficult to project. So we talk a little bit about that in the guideline. Then next, after we've given this foundation of climate models and climate data, we talk a little bit about some of the expected impacts on drinking water infrastructure. So we have a discussion on altered precipitation quantity, form and timing, changes to seasonal water flow patterns, and we talk about these in the context of how do they impact this infrastructure? How do these changes affect everything from water treatment to distribution systems? So warmer surface water temperatures, of course, has a big impact on water quality parameters. Rising sea levels, impacts on pumping stations, etc. We'd also talk about groundwater reserves. This is very important in Prince Edward Island. Drought, as Willard had mentioned, there have been droughts. And of course, water quality essentially is associated with all of these things. As you know, in every piece it comes into play, but we kind of try and pay a little bit of attention to it specifically as well because it is so important. And then what's really interesting for wastewater infrastructure, we've actually changed our approach a little bit. While we were working on this, we were made aware of this new CSA standard, S900.118, which is specifically a climate change adaptation for wastewater treatment plants. This is a really, really good document that's available. We can't copy this document or put this document into our guideline because it is a CSA standard. But what you can do is access this document, and we actually are going to recommend that people access this document and read it. There's also an 8-step methodology to identify climate change impacts in there, so it's a very strong document. Then we go on to climate risks, and here we really talk a little bit about top-down approaches and bottom-up approaches to identifying climate risks. The bottom-up approach is really another word for PIVC, and this is just a way in how you address a climate change impact on a piece of infrastructure. So, for example, it's the process of identifying climate change parameters that were going to impact your process, your facility, or your asset. And sometimes you can start this by looking at the asset first, or other times you start looking at the climate first. That's the difference between these two. And we recommend using the bottom-up approach, which is similar to PIVC. So although we can't use PIVC in our actual document because it is a separate process that has to be, you have to be authorized to use it. What we can do is identify a step to assess risk, a general framework. There are many, many frameworks out there. There's ones that are done through various US agencies and Canadian ones. We've adopted a bit of a hybrid here, and the document describes these steps in detail. And really what we do is, we use a 7-step sort of type framework, and we use categories to look at things like asset damage, financial loss, loss of service, health and safety, reputation, and those impacts based on climate change, expected climate change impacts. And then from that, a risk threshold map, so looking at occurrence probability versus impact severity to do a bit of a risk score exercise to determine which components of your process, asset, or project require climate change mitigation measures. So the final piece that we look at is giving a bunch of examples of adaptation strategies available for both water and drinking water infrastructure. The guidelines touch on a couple of things. First of all, we look at different things like watershed stewardship. We look at making facilities more flexible, being more prepared. We even look at more higher level water governance plans. Again, we just mentioned these, we describe them. We describe as well the cost-benefit analysis and multi-criteria analysis that can come into play when deciding to incorporate climate change resiliency measures. A lot of this has to do, at the end of the day, with available funding and budget. So the business case is extremely important. How does this climate change adaptation practices, how do they fit in with short and long-term needs? How do they fit into the works program? So again, what we're trying to do here is distinguish between the complexities of doing a full-blown climate risk analysis to going down on the ground and looking at potentially a small project and seeing how that fits in with that project. So The other thing we do as well, we provide this list of parameters and indices. So parameters are outputs from models, whereas indices are where you take output from models and you perform a bunch of calculations to derive specific parameters. Like, for example, the number of freeze-thaw cycles, or the duration of something happening, or the minimums or extremes. So these are values that are calculated from raw data, which are parameters from the global climate models. And we provide an example list of those. So usually indices are much more meaningful to decision makers rather than parameters. If you say this is the rain in 2050, it's not as useful as saying we can expect flooding to occur this many times in 2050 based on some of this rainfall data. So this is an example list of some of the key parameters that we really feel are important. Things like temperature, precipitation, but then these are indices, so you can see days with rainfall, days with snowfall, things like sea level rise. So these are kind of a list that we'll provide in the document for you. Finally, 5 sources of climate data, which are really important. And what we've done is we've tried to present a list of data which is, say, relatively complex and also relatively simple. So we increase the complexity of the data source as we go through them. So the first one is the Climate Risk Atlas of Canada. This is a relatively new tool. It is very user-friendly. It has a nice GIS sort of mapping interface online, and you can pick your community, and it just uses climate data from Canada's climate model, and you can pull off some initial numbers. So that's really kind of at a basic level, something that decision makers can use. It's easy to understand. And then we start cranking up the complexity of the data sources, but that also means more data and a lot more, I guess, information at your fingertips. So the Canadian Centre for Climate Modelling and Analysis, they have all the data available for download for Canada's climate models, which, of course, if you have some experience handling this kind of information and data, is extremely powerful. You really can then start to do your own analysis on climate data. Then, of course, everybody has probably heard of the IPCC, and they have a lot of really, really good resources available globally, which can be downloaded and looked at. And what we do in this document is we don't just tell you, go to this link. We talk about what do you find in these websites. We talk a little bit about how to use that data at those sources. So we try and kind of give some context. Then the Canadian Institute for Catastrophic Loss Reduction also has a lot of really good resources, a lot of data available. And then for water levels, like sea level rise, the Canadian Extreme Water Level Adaptation tool is excellent and is available for most communities on the coast in Eastern Canada. The other thing about these data sources is that we recognize they will be updated. We recognize that they are handled and stored by large national or international agencies. So in 5 years, there's no risk that these portals or this data will be no longer available, compromised, or out of date. So we did not want to put things in this guideline that we felt would be at risk of becoming obsolete, because that's the problem with climate data. It is very much a live thing that's constantly being updated. So some other considerations, I mean, this is a work in progress, right? We definitely know we need to continue working on this chapter. We've had some good commentary and feedback already. We want to include a bit more sophisticated discussions on doing potentially joint probability analysis, looking at probability of certain events happening, and then using a design life in that assessment to determine the tolerance to risk and to pick design parameters based on that. Of course, this is a living document, so it will be updated beyond this iteration in the future as well. So again, we're really focusing in this document on process and not so much on specific data points. So I'm just going to wrap things up here. I think I'm running out of time, but I think some key considerations at the end is climate information is never perfect, right? So it is truly something that is has a lot of variability. So it does require good judgment. It does require discussion. Really what we see as well in design is that, we don't necessarily care too much about sometimes the average conditions or day-to-day. We care always about these thresholds. these critical conditions. This can also be really challenging because these critical conditions are often really hard to model in the future. For example, IDF curves, or looking at, instead of IDF curves, looking at peak flooding events or peak extreme events. These are often not captured in climate models, so that's another challenge to think about. But on the flip side, very precise information is not always required as well. So with a lot of these PIVC assessments or risk assessments, you find that you don't necessarily need to know things to the day or to the millimeter. What you really need to know is understand the broader trends that are going to be impacting this facility, and having the ability to either prepare for that now or prepare for that in the future. And that's really also where the dialogue comes into play with the operators, the owners, the people maintaining this infrastructure. So really, again, it comes down to working together: engineers, owners, operators, climate scientists, and they really need to look at past failures and define these critical thresholds and work towards a sustainable and way of developing infrastructure that's climate resilient. Because of course we also don't want to add this unnecessary burden on operators and on funding sources. So that's really all I have. I think the main thing to take out of this too is, if anything, please go to our knowledge mobilization portal, download our draft, have a look. We are really excited to be getting feedback and to be making this your document, and very open to changing things as much as possible. So thank you so much. I really appreciate it. The time for everybody who came on today. It's quite a large group.